All right. So here is the same histogram that we drew by hand yesterday. Do you guys remember doing that? I want you to look a little bit further up on the page, or maybe it's a little further down. Sorry, I'm upside down from you guys. We said that we thought about how many shoes was typical for a student in this class. 10. We said about 10. But we didn't go in and actually calculate anything, did we? So there are two measures of center that we talked about yesterday, the mean and the median. And first of all, let me just start off by saying I think 10 is a really good estimate for what would be typical or what would be expected for a number of pairs of shoes for a student in this class. I'm going to scroll this down. Can you guys see this box over here? Can everybody see that okay? I know it's really small from over there. So this first number, or not the first number, the very first number is N. It was 19. What do you guys think that stands for? People. N is the number of data points that we have. So we had 19 people participate. The mean, the average, is 17.579. We'll talk about some of these other numbers, but this is the other number that I want to draw your attention to, the median. How do you calculate the median? Yeah, you put the numbers in order from smallest to biggest, and you cross out until you get to the middle. Our median was 8. We said a typical student in this class probably has 10 pairs of shoes, right? The median came out to be 8, which is pretty close to what we eyeballed this at. But the mean, the average, how do you calculate the average? Add them all up and divide. That's more than twice as big as our median. Why is there such a difference between those two numbers? Yeah, remember we had that 95 pairs of shoes? That took the average and pulled it way up away from the median. So 17.579, that's 579. And our mean was 8. The shape of our data was not symmetric, so we would go with the median on ours. All right, time for questions that have no wrong answers. Of the 3 types of data displays that I showed you guys how to do yesterday, which one do you prefer? Dot plot? Histogram. Does anybody like the stem plot best? Nope. All right, so those of you that chose dot plot, why do you like it the best?
It's easy to look at.
Easy to look at? Shows every exact data value, absolutely. Those of you that answered histogram, why do you like the histogram better? Looks similar to bar graphs, absolutely. Something else that I tend to like about the histograms, you don't have to plot every single data point when you make a histogram. You just have to figure out what bucket it goes into and take the bar up that high. So there's nothing wrong with which method you prefer. The stem plots are really useful like the dot plots are because they also preserve the data. They preserve the exact data that was used. And they can show us shapes similar to a histogram. They can show shapes similar to a histogram. So they kind of mix the best of both of those worlds. I would like you guys to jot down your answer to number 6 along with your reasoning on your page. I'll give you about a minute and a half to jot down your thoughts there. right. Let's go ahead and flip the page to 12. We had two big learning topics for yesterday. Underneath learning topic number 1, we talked about quantitative data. There's two types of quantitative data. So we have categorical data and quantitative. And then quantitative we can break down even more into discrete and continuous. Discrete data is a countable number of values. It typically does not have decimals. Continuous data, we have an infinite range of values to choose from. Dot plots and stem plots show every individual value. Histograms just show the general shape. The way we name our skewed distributions, we name them based on the tail. So skewed left has the tail on the left. Skewed right has the tail on the right. And then we have our symmetric graph. And then there's a picture of a bimodal graph over here. When we have a symmetric distribution, you will use the mean. And when you have a skewed distribution, you will use the median. When we describe a distribution, we use SOCS to help us remember. SOCS for variability or spread. We describe our shape. These are the typical words that we are going to use to describe the shape: skewed left, skewed right, symmetric, bimodal. Although you're going to want to use LY words as you're describing the shape. So roughly skewed left or approximately symmetric. If you're saying that a distribution is symmetric and you don't use like approximately or roughly, you're saying that it meets this very rigid definition, which it might not. But if you're saying it is approximately symmetric, you're like, it looks about like this. And that gets much easier for us to use in our descriptions. We want to describe any outliers. The center, based on the shape, we will use either the mean or the median for the center. And then we describe the spread as well. What was the only measure that we had for spread yesterday?
Range.
Range, yes. We use the range. We're going to learn about another measure of spread today and a third measure of spread tomorrow. We also have to make sure to get context in here. So including units with all of your numbers. What is the situation that we are describing? You want to make sure to get context worked into your descriptions of distributions. All right. Let's look at the check your understanding now. Mr. Wilcox is a huge fan of University of Michigan football. His favorite season was the 1997 season, a perfect season. The dot plot shows the number of points scored by the U of M team in the 12 games that season. I would like for you to use this dot plot to create a stem plot of the distribution. And if you need to flip back over to page 11 to remember what a stem plot is, please feel free. But I'm going to give you guys about 2 minutes to do a stem plot. Minute and a half, 2 minutes. Yeah, you can end it at 4.
that's not the histogram, how would you describe the shape? If that makes sense. Like if it's not showing it like.
If it's not showing it like that. So we're going to look at the stem plot that we've created right here to be able to describe our shape here in just a second. Yeah, turn it exactly like that. That's exactly what I do. Yes, Colin? Yes. All right, let's look at your stem plot. Stem plot should look something like this. Please make sure that in addition to having your numbers, it's okay on your stem plot to start where the data starts and to stop where the data stops. What you can't do, though, is skip any numbers in between those. So because my data starts at 14, it's okay that I don't start with the 0 because my data doesn't start until here. My data goes all the way out until 38, so I had to go at least to a 3. And if, let's just make this up for a second, if there were no scores that were in the 20s, I would still need a 2 as a stem, even if I don't have any leaves to go with that part. But it's okay to start where your data starts and stop where your data stops. Your graph, your stem plot, needs to be labeled. So we need to know what this is a graph of. This is points scored. And then you have to include a key with your stem plot. So my key down here, I have 20 dash or slash 02 slash 0 means 20 points. It does not matter what number up here you choose to make your key with. It can be the biggest one, it can be the smallest one, it can be one in the middle. The key that I'm working from right here has 23 as this key for the stem plot. There are a lot of times that stem and leaf plots get used for decimal values, where the leaves are decimal values, and so that's why it's so important to have the key, that we understand that our stem is the tens and hundreds place and our leaves are the ones place. That is what your key is for. All right, we're going to create something now that is related to a stem plot that I ask you to do on your homework that we haven't practiced yet. It is called a split stem plot. In a split stem plot, for every single one of the stems over there, we're going to double it. So 1, 1, 2, 2, 3, 3. For the top of each pair, you're going to put any leaves that are 0 through 4. And for the bottom number in each pair, you're going to put any leaves that are 5 through 9. Please go ahead and try to finish that out on your own. If you have questions about what I said, with the top number, it's leaves that are 0 through 4. And the bottom number is leaves that are 5 through 9. If you have any questions about how to complete this, please raise your hand. I'll be moving around the room to offer assistance. Okay, so your first number on here was 14. So when I'm looking at that, that would go from 10 to 14. So you're going to put the 4 right here. For this next one, if you had any numbers that were 15 through 19, you would put them here. But we don't have anything 15 through 19, so you'll leave that blank then. And then you'll come to your 20s. 0 through 4 goes here. 5 through 9 goes with the bottom. Back just in time. We're working on a split stem plot now. All right. So let's go ahead and put up what our split stem plot looks like. The 4 for 14 goes with the top one. We don't have any numbers 15 through 19 in the distribution, so I have a gap here. And then we record any values that are 20 through 24 with this first 2, 25 through 29 with the second 2, 30 through 34 with the top 3, and 35 through 39 with the bottom 3. Once again, you do have to label what this is a graph of. So it has to be labeled as points scored, And you do need a key to go with that. Please, please, please make sure that you have those pieces with all of your graphs, here and then here. Yes?
What's the point of the split? What does it do?
So,
In comparison to the other one?
in comparison with the other one, here we only have 12 pieces of data. I want you to imagine that we had 50 pieces of data, and what this would look like if I had 50 pieces of data, how long some of these tails would get. And in that case, doing a split stem plot kind of takes it, and instead of making it so long on the page, it kind of bumps it out this way. One of the things that it can also help us do is to determine shape. When we make a histogram, you were one of the people that preferred a histogram, right? I absolutely prefer histograms also. When you're looking at a histogram, we have to decide on our bucket sizes. How big are our buckets? So yesterday when we made our histogram, we counted by tens for our buckets. That is what we're doing when we do a regular stem plot. If we do a split stem plot, it's like a histogram with buckets of size 5, so it's like counting by 5s. Because this one goes from 10 to 15, this is 15 to basically 20, and then 20 to 25, 25 to 30, and so on. Does that help?
Yeah. So it's for like bigger?
For bigger data sets or to better determine the shape. Bigger data sets or better determine the shape. Speaking of shape, that is the next question that we've been asked, is to describe the shape of the distribution. We can look at dot plots for shape, but sometimes it's really hard to tell the shape from a dot plot. Like when I look at this dot plot, most of these just have one dot, like all the way across. I have a hard time seeing shape here. When I look at this stem plot, now when I look at my stem plots, I'll often take my paper and turn it sideways, because then it looks more like a histogram. These look like bars that go up as far as my histogram would go up. Or you could do that with the split stem graph. We can see that we have a gap here on this one. I don't see the gap when I look at my regular stem plot, but I do see the gap when I look at my split stem plot. Overall, would you guys describe this distribution as being skewed left, skewed right, or approximately symmetric? I would go with approximately symmetric on this one. I do think there is a slight skew there, but I think it is so slight. Like here we only have 2 extra data values versus the 1 right there. I think it's such a small difference. And especially when I look here, I see the big bump of data in the middle, and I see these tails that are reasonably equidistant from that big bump of data. So I would call this approximately symmetric, or roughly symmetric. I would never, ever, ever call a distribution just symmetric. I'm always going to soften it up. Are there any potential outliers? Let's go back and look at the dot plot for this one. Remember, outliers are going to be far away from most of the rest of my data. Is there anything up here that you say, like, that might be an outlier? 14 looks like it could be an outlier. Anything on the other end? Yeah, like the 37, 38 could possibly be outliers as well. So possibly 14 on the low end, maybe 37, 38 on the high end. We are going to get a rule for outliers tomorrow in lesson 5. With me, dear? Hang with me. When did we say we wanted to use the median to describe the center? When there's a lot of outliers, or when it's skewed left or skewed right. When do we want to use the mean? When it's symmetric or approximately symmetric. So given our data set, what measure of center would be most appropriate to describe this distribution in the check your understanding? The mean. Why?
Because it's approximately symmetric.
Yes, we described this as approximately symmetric or roughly symmetric. All right. For the rest of what we're going to do today, you are going to need a calculator. If you don't have a calculator that you prefer using, please feel free to come and grab one of my yellow ones. It's going to make the calculations a lot faster than trying to use your cell phone calculator. If you have your own, you're welcome to use your own. If you really, really, really like your cell phone calculator, I'm not going to stop you from using it. Right. Which city has the better weather? Both Denver and San Francisco are desirable locations to live, but which city would you say has the better weather? Below is a dot plot of the high temperatures from a random sample of 6 days from each city. So here I have a 6-day sample for Denver and the high temperature on those days. And here's a 6-day sample for San Francisco and the high temperature on those days. Question number 1, what is the same about the high temperatures in each city? What is different? I want you to think about that acronym that we have to describe distributions. Do you guys remember when we talked about SOX? What's the first S stand for?
Shape.
Shape. The O?
Outliers.
Outliers. C?
Center.
Center. And the second S? Spread or variability, yes. And if you say variability when I ask what the second S stands for, that's perfectly fine. I know it's not an S word, but it does stand for spread or variability. It's just SOCV doesn't stick in my head like SOX does. All right, so I want you to think about SOX. Think about the things that we describe. If you look at these two distributions, which pieces of SOX, shape, outliers, center, spread, looks the same between the two, and which pieces look different? Centers look the same. The centers are about where? Yeah, somewhere between 60 and 65. Certainly seems to be centered right around 65 for both of them. What's the biggest standout difference between these two? Yes. The spread, the variability. Which one is more spread out? Denver, we say it has higher variability. The more spread out it is, we say it has higher variability. The less spread out it is, the lower the variability. All right. So they have similar centers around 65 degrees Fahrenheit. In San Francisco, the data is more clustered, and in Denver, it is more spread out. One way to measure the variability for a data set is with the range. We did that yesterday. I want you to calculate the range for each city, and I have added up here, you can see those dots on the ends. On the low end for Denver, that farthest left dot is at 44. On the high end for Denver, that farthest right dot is at 89. For San Francisco, the farthest right dot is at 71. So what is the range for Denver? 45. 45 what? Degrees Fahrenheit, yes. So do you guys remember when I said we have SOX plus context when we describe our distributions? Including units on any number where it makes sense to include units is one way that we get our context in here, that we make sure that we get those points. What is the range for San Francisco? 11 degrees Fahrenheit. Thank you for adding those units on there. All right. Another way to measure the variability is the average distance of the values from the mean. The average distance of the values from the mean is the same thing as standard deviation. And we are going to calculate the standard deviation for Denver. So part A right here says complete the table for the Denver data. The mean is 65 degrees Fahrenheit. So the first thing that we want to do for each of these values is calculate how far is it from the mean. So I'm going to take my value, so in this case 44. I'm going to subtract the mean, so minus 65. What is 44 minus 65? Negative 21. You're going to do that for every single data value in this table. We're going to do 51 minus 65. What is 51 minus 65? Negative 14. Please do that for all the remaining values in the table. We're calculating the average distance from the mean. So the first thing I'm going to do is just figure out how far are each of these data points from the mean. Once you've calculated all of those distances, you're going to take the distance from the mean. So for this first one, that would be negative 21, and you're going to square it. What happens to any number when you square it? It becomes positive. If you don't use the parentheses on a calculator, it will not force it to be positive. You want to make sure to use the parentheses on the calculator. What is negative 21 squared? 441. And then the next one we had was negative 14. What is negative 14 squared? 196. All right, I would like you guys to finish this table out all the way through 89. Stop when you get to the total row. Once you have all of these squared values over here, I want you to add them all together. Once you have all of the squared values, I want you to add them all together. What did you get for the sum of all the squared values? 1,454. Perfect. We want to calculate the average distance from the mean. How do you calculate an average? You add everything up and you divide by however many numbers you had, right? In this case, we have how many numbers? 6. So I want you to take this 1454 and divide it by 6. What do we get?
242.33.
Yes, 242.33. That is close, but not quite there. That's the average of the distance from the mean squared. I don't want the distance from the mean squared, I just want the distance from the mean. So what would I still need to do to this number? Square root it. So please go ahead and square root that number. Yep, square root 242.33. What do you get? 15.57. We're writing that down right over here. This is the average distance from the mean. All right. I'm going to flip back over to that same app that I used to crunch the data about our shoes. And I'm going to use that to calculate these summary statistics. So I'm going to put that box up on the screen again. I want you to copy in what we get. All right, here we go. So I've got 44, 51, 61, 65, 80, and 89. Those are all the days, right? All right, begin our analysis.
We're filling this in number 4, right?
Yes, you're filling this in the box in number 4. So n is 6. The mean is 65, but we already knew that. Underneath where it says SD, we're going to put 17.053. The minimum is 44. Q1 is 51. The median is 63. Q3 is 80. And the max is 89. So that I can make that just a little bit bigger on the screen. I've got that filled in right down here now. So SD stands for standard deviation. We calculated the standard deviation to be 15.57, but when we used the applet to calculate standard deviation, it came back with 17.053. So let's figure out what's going on here. What's happening is that they have to allow for a little bit more variability in the applet, and this is the way all of the programs calculate standard deviation. Instead of dividing by 6, which was the number of pieces of data I had, back here when they did this division, they divided by the number of data values we had minus 1. So I want you guys to come back over here, this 1454, grab your calculators for me. 1454, instead of dividing it by 6, I want you to divide it by 5. Take 1454 and divide it by 5. And now I want you to take that number and I want you to square root it. You should have gotten 290.8 when you divided by 5. And when you square root that, you get 17.053. 17.053 is exactly what that applet had calculated our standard deviation as. So when we calculate standard deviation, there's this process that we're going to go through. Each of my individual values we call the X values, and it gets an I right next to it. The I stands in for a number. So X1 would be this first piece of data. X2 would be the second piece of data. X3 would be the third piece of data. X4 is the fourth piece of data, and so on and so forth. We use I to represent the fact that I don't know how long this list is going to be, but there's a lot of data on this list. So calculating standard deviation, the first thing we do is we calculate how far are each of those data values from the mean. X bar here stands for the mean, the average. And then we take that and we square it. After you take each individual data value, you subtract the mean and you square it, we had to add them all up. Have you guys ever seen a symbol in math that means to add a whole bunch of things up? Yeah, it looks like a sideways capital M. It's a capital sigma. Here is what the official formula looks like for standard deviation. Here's each piece of data that I have. I'm going to take each piece of data and I'm going to subtract the mean. And then I'm going to square it. Then I'll take my next piece of data and subtract the mean and square it. Take the next piece of data, subtract the mean and square it. Then I add all of those up. I divide by however many numbers I have minus 1. And then I square root at the very end.
What's the point of squaring it if you're just going to square root?
That's a great question. What do you guys think? What's the point of squaring it if we're just going to undo it at the end? What does squaring accomplish? Forces it to be positive. So the reason that we want to do that is I want to know how far away typically are these numbers from the center, and I don't care whether they're farther away to the left or farther away to the right. But if I don't square them, then those numbers that are farther away to the left are going to end up negative numbers. And when I add those with my positive numbers, it's going to make it look like these numbers are much closer to the center than they actually are. Does that help?
Yeah.
Okay. All right. We're going to add one more day to the data set. A very cold day in Denver where the high temperature was only 7 degrees Fahrenheit. So we're going to add that value to the data set, and we're going to record a new set of summary statistics. This is going to go underneath number 5. We're going to edit our input. We're going to add one more day where the high temperature was only 7. We're going to begin our analysis. All right, so now to fill in that box underneath number 5, n is now 7. The mean is 56.714. The standard deviation is 26.887. The minimum is 7. Q1 is 44. The median is 61. Q3 is 80. And the max is 89. Let me get that up on the screen. There we go. So what changed between these summary statistics and the summary statistics in question number 4? What changed? The mean changed a lot. The mean decreased. The minimum changed. Standard deviation went up. Did anything happen to the median?
Yeah.
What happened to that? It went down too. So the mean and the median both went down. The mean decreased a lot, more than the median. Standard deviation went up. We say that the mean is non-resistant, and we say that the standard deviation is non-resistant. They are easily influenced by outliers and skews. Okay, we're almost done. Easily influenced by outliers and skews. Have you guys ever seen a really stubborn toddler? If they don't want to do something, they just like throw themselves on the floor and they're not moving. A stubborn toddler would be resistant to change. The mean and the median are non-resistant. They are very easily movable compared to the median. Last question that we're going to do for today, we'll do the backside of this tomorrow. How would the average distance from the mean for San Francisco compare to Denver? Do you think it would have a higher standard deviation, a lower standard deviation, or approximately the same standard deviation? Smaller, yes. Not as spread out means a smaller standard deviation. It's actually much lower. The temperatures in San Francisco don't vary as much. And because I had the time, I actually went in and calculated the standard deviation for San Francisco using the applet. The standard deviation for San Francisco was only 3.633, much closer to the mean. We will do page 14 tomorrow. What else is going on tomorrow? Homework is due. Yes, homework number 2 is due. Even though we did not finish the check your understanding on page 14, there's nothing on homework number 2 that we have not gone over in some form or fashion how to do, or that is not in your reading somewhere. Please make sure to do that reading.
Is there